Hello everyone. In the previous video, we had learned about implementing simple linear regression using Scikit-learn. In this video, we'll be studying classification with Scikit-learn. A classification problem is when the output variable is a category such as red or blue, disease or not disease, or spam or not spam. Right. So a classification model attempts to draw some conclusion from observed values. Given one or more inputs on classification model will try to predict the values of one or more outcomes. For example, when filtering emails, spam or non-spam, when looking at transaction data, fraudulent or authorized. Now, there are majorly two types of classification problems. The first one is binary classification. Now, this is the typical example of email spam detection, wherein if the email is spam, then we give it the value as 1. And if the email is not spam, then we give the value as 0. The second one is multi-class classification. This can work for handwritten character recognition, where classes can go from 0 to 1. Now, the main difference between regression and classification algorithm is that regression algorithms are used to predict the continuous values such as price, salary, age, weather, etc. And classification algorithms are used to classify the discrete values such as male or female, true or false, spam or not spam, etc. Now, the different types of classification models are knife-based, stochastic gradient descent, k nearest neighbors, decision tree, random forest, and support vector machine. In today's lecture, we'll be starting with knife-based theorem. A knife-based classifier is a probabilistic machine learning model. Using knife-based theorem, we can find the probability of, as given in the formula, probability of A happening, given that B has occurred. Here, B is the evidence and A is the hypothesis. Now the question arises, why is this name knife-based given? It is named knife-based because the assumptions made here is that the predictors or the feature values are independent, which means that the presence of one particular feature does not affect the other, and hence the name knife. Now, to understand the other formulas, Bayes' theorem can be written as given over here, where it has been given P of y given x equals to P of x given y multiplied by P of y divided by P of x. The variable y is the class variable. Example, if it is suitable to be not spam. Variable x represents the parameters of features. Now, x can take multiple values between 1 to n, and those have been substituted in the second formula, as you can see over here. So, in the first formula, we have substituted the various values of x from 1 to n. Now, we are not interested in the exact value of x, as we are interested in relative relations with the other probabilities. Thus, we can only compare the numerator as the denominator is same. And that is how we are coming forward to the third formula. There could be classes where classification could be multivariate. Therefore, we need to find the class Y with maximum probability. Now, this is the final formula which will be used, and we have omitted the denominator here. Now, the different types of knife-based classifier. The first one is multinomial knife-based. This is mostly used for document classification problem, that is, whether a document belongs to the category of sports, politics, technology, etc. The features or the predictors used by the classifier are the frequency of the words present in the document. The second type of knife-based classifier is Bernoulli knife-based. This is similar to multinomial knife base, but the predictors are Boolean variables. The parameters that we use to predict the class variable take up only value yes or no. For example, word occurs in the text or not. The third type of knife base is Gaussian knife base. When the predictors take up a continuous values and are not discrete, we assume that these values are sampled from a Gaussian distribution. Since the way the values are present in the data set changes, the formula for conditional probability changes too. This approach is built on the assumption of normal distribution of probabilities. Now, one of the very important factors under knife base is Laplacian correction. At times, it can happen that the numerator will give us zero value, right? But and then thus making the probability zero. But at times, it does hold some significance and some importance, and we just cannot neglect that probability. For this reason, we use Laplacian correction. In this, what do we do is we add +1 to the numerator, and to the denominator, we add the number of distinct features. Understanding all of this, now let us move forward to the coding part. These are the important libraries that have been imported. The first one is train test split, wherein we are splitting the data set and we have taken iris as our data set. Thereafter, we'll be calling the multinomial Gaussian and Bernoulli knife-based models, and thereafter metrics. As we had discussed earlier in the earlier videos, we will need some metrics to measure that how well our model is performing. These metrics does the same part. The first thing is Gaussian knife-based. Now, this is the formula for Gaussian knife-based theorem. We have loaded our data set. We have split it. We called the Gaussian knife-based. We are fitting our X and Y values in that. And then we are predicting the X test values. Thereafter, we are computing the prediction, accuracy score, classification report, and confusion metrics. So this is how the output for our Gaussian knife-based comes. The similar way, we have multinomial knife-based classification, and thereafter we have Bernoulli knife-based classification. Now we took the same data and we have applied it on 3 different knife-based. Let us compare the results that we are getting. In case of Gaussian knife-based, our accuracy score is 100%. In case of multinomial, it is 97%. And in case of Bernoulli, it is just 35%. So why is this case? Let's jump back to the definitions that we had talked about. Bernoulli works with only 2 kinds of class, yes or no, right? But in our case, we have 3 class, which is iris sectosa, iris versicolor, and iris virginica. Thus, the problem that we are trying to solve does not fit with the definition of Bernoulli knife-based, and that is how it is giving us wrong results over here. But you might ask, in case of multinomial, we do have 3 classes, and it fits well with the multinomial knife-based classification also. But just to give the weightage of the Gaussian distribution nature of the data set that we have in our iris data set, the Gaussian knife-based model gives us better accuracy score than knife-based classification model. Now, in the example, in the output, you're seeing what accuracy score is. Classification report has precision, recall, F1 score, and then we have confusion metrics. So what all are these terminologies? So accuracy is the most intuitive performance measure, and it is simply a ratio of currently predicted observation by the total observations. Thereafter, we have precision, recall, and F1 score. Before understanding these terms, we have to understand four other different terminologies. The first one is true positive. So I'll simultaneously write over here. The first one is true positive. So true positive are the correctly predicted positive values, which means that the value of actual class is yes, and the value of predicted class is also yes. Thereafter, we have true negative. Now, true negative, these are also the correctly predicted negative values, which means that the value of actual class is no and the value of predicted class is also no. Thereafter, we have false positive. When the actual class is no and has been predicted yes, then that comes under false positive. And thereafter, we have false negative. This happens when the actual class is yes, but predicted class is no. That is how we'll come forward to precision now. So precision is nothing but the ratio of correctly predicted positive observations to the total predicted positive observations. Now, in terms of words, it sounds kind of messy. Let us just write it in the form of formula to help you out. So it is the ratio of true positive divided by the ratio of total predicted positive observations, which is true positive, and thereafter we have true positive plus true negative. Sorry, it is false positive, as we are taking the total predicted positive observations. Thereafter, we will have recall. Now, recall is also called as sensitivity, and it is the ratio of correctly predicted observation values, the positive observations, to all the observations in actual class. So let us write down this in the form of formula. So it is true positive divided by true positive plus false negative. So this is what our precision and recall is. Next comes F1 score. Now F1 score is the weighted average of precision and recall. Therefore, this score takes both positive and the false negative into the account. So F1 score can be written as 2 into recall into precision, and we'll just add this into a bracket. This will be a numerator, and our denominator will be recall plus precision. This is our F1 score. The next thing that we are seeing in the output is called confusion matrix. Now, the confusion matrix is the summary of prediction results on classification problem. So if we have just two classes, then all of these will represent the true class and the rows will represent the predicted class. And if we have two classes, which is positive and negative, all the diagonal values come under green and the rest of the values are under red, which we don't want. But in our case, we have three classes, which is iris, setosa, versicolor, and virginica. Then how do we calculate the confusion matrix? Thus, in our case, let me just move to the Gaussian light base. In our case, the first row is iris sectosa, the second is versicolor, the third is virginica. The first color is the first column is setosa, second is versicolor, and third is virginica. Now, all the diagonal values are the green values, and rest are the red values, which we don't want. In our case, all the values, in the case of Gaussian, all the values lies in the diagonal, and that is how our accuracy score is 1, because none has been predicted into a wrong class. In case of multinomial naive Bayes, there is this one data point which has been predicted wrongly. So we can say that predicted class is iris versicolor and the true class is iris virginica. And that is how one data point has been predicted wrongly. In the case of Bernoulli knife base, only the first setosa has been correctly predicted. Rest all the values are predicted wrongly, and that is how we are landing up to the accuracy score of just 35%. That is all for today. Do let me know if you have any questions in the comment box. Have a great day.